Okay, hello everyone. Welcome to the latest in our season of design reviews, getting ready for Wolfram Language version 13. And the first one we have today is a continuation about graph theory, I think, or maybe it's
geometry and graphics.
Okay, fine. All right. So let's see. We had been looking previously. Has this been updated?
Yeah. Okay. That's the new name we came up with.
Okay. All right.
Then the next two, gradient mesh was called Poisson mesh, and ball mesh was called concave hull mesh.
Were those the names we agreed on last time?
No.
Kind of like gradient mesh, or at least something like it.
What does it mean?
Oh,
I mean,
there's also the chance of gradient fit mesh because we are fitting the gradient.
And that will be ball fit mesh.
Yes, or concave fit mesh because you're
no, concave is no way.
Okay.
We're not fitting concavities. We're fitting. What about other meshes? Aren't other meshes also fits? What other meshes do we have? I mean, Delaunay mesh.
From points is Delaunay mesh and Voronoi mesh. And they're duals, but they also have a geometric construction from the start. Voronoi is basically an optimization description. It's a nearest description.
Yeah.
But now I guess neither of those are mesh reconstruction methods.
Yes, they are.
Yeah.
Well,
yes, they are.
But last time,
they are. Yes, they are.
No, like if it's like you have a mesh and you sample a bunch of points from it, these other reconstruction methods all are supposed to give you those meshes back. These give you a different mesh. They're just functions from points to meshes.
What was the name we came up with last time? We came up with something reconstruction mesh, right?
It's down
what was
there
the name?
For the future, reconstruction mesh.
And it's the idea that like in the future, there'll be a big function that just does these automatically and maybe has other methods too.
Yeah.
Why?
We can't do that now, but we can do that in the future.
And because also reconstruction is kind of an ill-posed problem, right? I mean, so we need that general function will have a lot of heuristic and
it needs goals. What's the goal of the reconstruction?
I mean, I would argue if it's
not just different methods that do the same thing. There are different goals. Should it be closed?
Well, reconstruction, yeah, right. But it has certain properties. It's not going to be able to necessarily do a perfect reconstruction. By the way, I assume I can look for ball mesh.
But hold on. I mean,
where is it? Sorry, can I find this, please? Where is it?
Concave hull mesh.
Yeah, it's still called concave hull mesh.
I mean, I would argue though there's still a division between something like Delaunay mesh or especially Voronoi mesh and these other reconstruction things because they're not reconstructing anything. They're just constructing something.
You're right, Christopher. But there's a goal, okay? What's the goal of constructing a Voronoi mesh? It's a different goal than some other goals.
For sure,
and if you look at reconstruction mesh, I mean, we kind of start to explicitly document those different goals and constraints. So you need kind of a language to describe what you want at the end.
I have a spelling mistake there in reconstruction.
Yes.
It's an R missing.
Okay, but so. Okay, this is a crazy thing to say. I mean, either we're saying you grow a ball from every point. Is that the correct thing? Is that what it's actually doing? What is it actually doing?
Well,
because one thing, you could end up with sort of a balloon dog type thing, right? Where you just grow in a puffy ball from every point. Is that what this is, or is that not what this is?
No. So like you see here, it's just roughly speaking, if you think about it like a subgraph of the Delaunay mesh. So you have a Delaunay mesh, and then essentially giving a ball of radius alpha, you see if those edge of the Delaunay mesh fit inside that ball, and then it's those edges you're actually picking.
Okay, I absolutely do not believe in this title, in this name, ball mesh. Then I absolutely, profoundly do not believe in it, because I would expect a balloon dog.
Well, no, it's equivalent. Okay, maybe the balloon dog is a different thing, but it's equivalent to if you grow a ball from each vertex, where and you select all the, you only keep the Delaunay edges to other points that are within that ball.
Right, but what I would expect for a ball mesh is a mesh made from a bunch of spheres. Right, we could imagine doing that. That would be a perfectly reasonable thing to do, right? Imagine.
No,
Yes.
the mesh is piecewise linear.
Well, I don't care. I mean, it's
whatever.
whatever.
You can do a region union of a bunch of balls, but it usually is kind of not very good.
Useful. It's not useful, right? But I just don't think that's the right name, because I think it suggests the thing's going to be made from balls. Okay, and your piecewise linearity statement about meshes is a very parochial statement. I mean, I don't know. Go ahead.
This was kind of a temporary name, and for sure, ball mesh can be ambiguous, especially that, I mean, there are some places actually, instead of generating piecewise linear mesh, you actually look at the same places, curved same places coming from balls. So there's also that possibility in long term, which can be ambiguous.
Okay, but hold on. So explain this to me again.
A simplex is very well defined. What did you say?
Well, no, you assume same places are in our standard definition, right? Same places.
Yes. Simplex is a simplex.
Right, which is linear, but there's generalization of same places which are not limited to linear cells.
Okay,
which is not
what I mean.
Let's go through this again, what this is actually doing. Okay? What this is actually doing. So it is, go ahead, explain it again, what it's doing.
Charles, look at the construction on the left. You draw a ball.
Right.
Yeah.
So it's essentially you have a set of points, you construct the Delaunay mesh, right? So essentially which allow you to find the closest neighbor, right? So you get those triangles pretty much in 2D, right? And then you cover those triangles with balls passing through, 2 points. And if those edges are actually inside the balls, then you consider them. So that's kind of the illustration there.
So what about something like but the Delaunay mesh, I don't understand this. You construct a Delaunay triangulation, and it's kind of like the boundary Delaunay. It's some kind of boundary of that Delaunay triangulation. Is that right?
You should go to the Delaunay mesh documentation so you can see what one of them looks like. Right. So I mean, it basically just it makes it just triangulates all the points, and you just have sort of the right. I mean, you can see.
But
if you just look at
this
that.
is the exterior, or this in the interior of this object. Is it also triangulated, or this is just the exterior?
No, it's the interior. That's a 2D thing.
Okay, but what about the 3D case?
In which case you have simplices, tetrahedra.
But you're triangulating the whole volume, right?
Yes.
Yes.
Whereas, so the interior is all filled for the Delaunay mesh.
Whereas this thing here is the boundary of that, right? It is merely the surface. Am I correct?
There are cases where you can actually have a hole inside. So let's suppose like those set of points are far enough that in the middle there is a hole.
Okay, fine. All right, but this is essentially what you're telling me is this is finding the boundary of the Delaunay mesh.
No.
Correct?
I think not.
No, it is not.
No. Okay. So are you telling me that this is selecting certain what from the Delaunay mesh?
Certain edges.
So imagine certain edges, right? And so imagine if you have that Delaunay mesh there. I mean, maybe if there was a documentation picture of like points sampled from like an annulus or torus or something, that would be great. But I don't know if there is.
Well, let's just do it. I mean, go ahead.
Well, okay. I mean, the point being, if you did it right, you'd find that there'd be, there'd be all these little points along the actual body of the annulus, and then in the middle there'd be a couple of giant triangles with really long edges. And so all this is doing is it's just deleting the really long edges and their sort of associated triangles. I would do an annulus because it'll be much easier to see what's going on.
Do we have an annulus? Yes, we do.
Yes.
Okay, default annulus, let's take 100 random points in the default annulus. And then let's say Delaunay mesh of that. Oh, for goodness sake, what is that? What happened there? Why did it not do that? Hello?
Probably it's a prototype build. Probably there's some issue lately. So probably use the master branch.
I don't drink wine, but that's another place where this, let me get a 1952 vintage, whatever. Never mind. Okay, what? It's the wrong vintage. What's that?
Oh.
I'm not drinking the right vintage here.
I see. Okay.
Never mind.
Right.
And now I have the stupid zoom window on top. There we go. Okay, let's try this again here. Okay, there we go. I see. So.
And if you had even more points, it would be even more obvious.
Okay, all right. So now what is this thing going to do?
It's going to delete the edges that are too long, and then their associated triangles are also going to disappear. So for example, that big edge in the middle is, let's say, bigger than R. It's going to delete that, and it's going to delete the two triangles on either side of it, I think.
Okay, well, so is it in fact a filtered Delaunay mesh?
Yes, you can look at it in terms of graph, like you will generate a subgraph.
What is the name that's in here? Is it concave hull mesh or is it ball mesh?
Concave hull mesh, I think.
Concave hull mesh.
Why is it not changing color?
Probably needs the documentation. I don't know. No,
that's not changing color either.
Did we change the name?
That seems to know about that.
Wait.
It's more modern than we are. Oh, for God's sake, why isn't that working? Okay, so what would we see if this worked? We would see the same thing, but without those interior edges. Is that correct?
Correct.
No, we wouldn't see the same thing. We would only see the boundary. We would just see chunk around the boundary, right?
No, it will. So it will probably delete the interior edges, like the big. You have three large triangles there in the middle.
Okay, and so that will be white in that area. Is that correct?
Correct. So you probably have a pretty much.
Can you run this on your machine right now? Do you have a version that actually works?
We don't have an implementation of the 2D. The 3D work. So I'm sure that's probably the problem on your build.
Okay, so if I do the same thing here for a torus, that won't be a torus, but we could do a torus anyway. Just crash.
The answer is though is it does keep the interior cells. Like, I mean, it deletes certain things, but it fundamentally is keeping the interior. It's not just the boundary.
Okay. So really, it's a filtered Delaunay mesh. Is that a true statement? Whatever's happening is, it's just the Delaunay mesh with certain simplices removed, correct?
Correct. Or he used the Delaunay mesh to reconstruct the region. But
arguably, I mean, if it is keeping all the interior stuff, and maybe it doesn't have to, but then you're not really trying to reconstruct the original mesh, because the original mesh, doesn't have all this interior action, right?
So the key idea is the following, right? So you have a set of points, right? Your usual approach is, when you want to construct a polytope or polygons, right? You use the convex hull. But your original set is not always convex, right? So the best way to do it is essentially you look at close by point, right? Some kind of clustering, and essentially you select edges which are close by with a certain radius. And so that's pretty much the idea. So that's why you actually cover those points by the ball. And then
I understand, Charles. Right. What I'm trying to get to is the output, if it was working correctly, would be this thing with all its little shattered glass effect with white in the middle. Am I correct, yes, or am I not correct?
Correct.
Okay, white in the middle, correct?
Correct. Close to the annulus in 2D, yes.
Okay, fine. All right, with the interior shattered glass stuff, yes?
Yes.
Unlike convex hull mesh, which only shows the exterior, right? So this would be completely, concave hull mesh would be just completely the wrong name, right? Because if we compare these two, right, this one, it really is an interior covering mesh with certain things deleted, right?
So maybe, I mean, is there a fundamental reason why it should, or why it should keep the shattered glass stuff and why it couldn't just get the boundary mesh?
I think for many reasons it's better to keep a boundary representation rather than a full mesh representation.
Well, but
because
that's not what it's
computationally
doing right. But that's not what it's doing. It's keeping the internal shattered glass, right? In the current description of what you say it's doing, it's keeping that, correct?
Yeah. I mean,
yes.
I think we need. But let's think about sort of which is the best, most useful representation.
Well, I think they might both be useful.
I think they might both be useful too.
No, that's not possible. So that's the key thing, is that you cannot always have both representation, a boundary representation and a mesh representation, right? The technique of construction, which is a specific one, unless we decide to change that technique, right? Essentially, you are looking at the cells. In the dimension 2, you have the triangles. In dimension 3, you have the face, triangle in dimension 3. And then you group them. Especially on dimension 3, it's obvious that you cannot actually build a tetrahedron. So you cannot actually just describe the boundary.
Are you saying it's a 2D surface in 3D?
It's a 2D, yes. All those reconstruction techniques are purely surfaces, right?
Wait a second. So this reconstruction mesh would be a surface in 3D, correct or not correct?
It could be. It doesn't have to be, it sounds to me.
Yeah, the plan for reconstruction mesh, right, since we will have the constraint, is that you can actually say you may want a full dimensional, a non-empty, a full dimensional region, and then we can generate you. So that's why that function will be more general. And we need
so wait a second.
So wait, is the point that basically you can end up with lower dimensional stuff because it's deleting edges, not simplices, right? So it's like you might delete. Let's say you have a triangle. If you delete 2 of the edges, you might end up with a point on its own and a line on its own, and those get kept or those get deleted or something.
So you mean for which case? For this concave hole mesh, or you mean
for concave hole mesh?
No, you always get the cell of the coming from the Delaunay mesh. So the triangle.
But so I guess right. But let's say you have 3 points. You get their Delaunay mesh. It's some trivial triangle, right? And then let's say 2 of the edges on that triangle are longer than alpha, and so they get deleted. Does that mean that the result is going to be an empty region, or is it going to be a point with a line or something like that?
So the standard case is that people say it should be an empty region. It will be an empty region. Like right now, we'll return an empty region.
Look.
Okay, but so I mean, how in 3D do you end up with triangles and not simplices as cells, or is that not? Yeah.
Because if somebody, for example, sample a sphere in 3D, right? So you have a surface and then you want to reconstruct it. It'll purely be that surface.
Okay, let me make some suggestions.
But what if you sample a curve in 2D? Will it be that curve?
Well, it won't be with a Delaunay mesh. If it's a filtered Delaunay mesh, the curve will not. Look, let's do it.
This is what I was asking, though. I mean, the question is basically, if you delete edges, right? Like if you had your curve and you deleted all the edges that were too long, and you were just left with the edges that go along the curve, and those that's a one-dimensional object embedded in a 2D space. And the question is, does that get deleted? And I think you said the answer was yes, it does.
What
so
should
I guess
this
then
do? What does this do? What would this do? Because anything you remove here is going to give you garbage. It's not going to give you, there's no way to get just something like the circle.
No, there is, because there are edges that are going along the perimeter. So if you kept lower dimensional stuff, you would get a one circle or whatever.
Sorry, say that. Yes, I understand that. Right, I understand that. If you keep the lower dimensional thing, but as soon as you're keeping complete cells, you're toast here.
Well, but you are also trying to reconstruct a one-dimensional region, right? So,
what's your point?
I mean, if we're basically saying that if this function is only for reconstructing regions in the embedding dimension, then it's sort of like, sure, then it's understandable you wouldn't be able to do that.
Charles, is it? And how does it then relate to reconstruction mesh? Which one lives only in the embedding dimension, or is it both, or is it neither?
So it's both. So this function is just a specific technique to try to reconstruct shape, right, with a hopefully certain concavity, right, to preserve what?
No. Let's be specific about what it is. In this case, it's a pity the function doesn't work right now. In this case, what would it do? Will it remove?
In this case, it will reconstruct. So for a given alpha, so if, this is a sample point of a circle. So if you take it with a descent for a given specific radius, it will reconstruct the circle. For a certain large.
No, you won't. No, you won't. There are no cells on this boundary. All the cells here are these things that go across the diameter.
No. So, right. So you have a random. So you sample around, circle uniformly, right? Mm-hmm. And essentially, between those circles, the Delaunay mesh actually connected the boundary. Plus, you have those long, long triangles.
But hold on. So you're claiming on the boundary here. Can I say boundary mesh of this? Will I get the boundary?
Yes.
It'll just be a convex hull, though.
So what is that? Is that a single? Is that a single mesh?
I think there's a theorem that says that the boundary mesh of a Delaunay mesh is the convex hull. So that is the convex hull.
Or maybe
but boundary mesh works generally.
Here you want region boundary, right? Is what you want.
If you just want the boundary, you get region boundary. So that applies to general regions, not just meshes.
Okay, so region boundary of %4. Okay, there we go. All right, so that, you're telling me those are a bunch of little micro cells. Is that correct?
Yeah, a line segment is a cell.
No, but is it a cell in the right number of dimensions? That's the question. Is it a cell in dimension 2 or not? Because what we're saying is this function is selecting cells in the embedding dimension.
No, I think that this is where we got confused.
No.
What Charles said, if you're going to reconstruct a surface in 3D, a surface is not of dimension 3. It's of dimension 2.
Yes.
So it's not the same as the embedding dimension.
Okay.
And a curve.
Okay. So but you're totally confusing me. This thing here, you told me that your ball mesh construct.
But that's what is confusing, because it's in this case it reconstructs the same dimension as the embedding dimension.
Okay. So we got to decide, because either
it's not hard. It's
surface.
So you see, is that the annulus have an interior, right? So if you sample the point, you sample the annulus, you have the interior point. Right, so it'll be possible to reconstruct the triangle inside the interior, where in the case of your circle there, right, the circle doesn't have interior points, so that's why you have those long edges connecting to the other side. So for a given alpha, you will not be able to carry those edges, so you'll end up with just the boundary.
So this coarsened Delaunay mesh can return things which are not in the mesh. Is that correct? which are not in the full dimensional mesh. Is that correct or not?
No.
Okay. Then how is it returning? Would
those
this
line segments
Delaunay
are
mesh,
in the mesh, Stephen? Those line segments are in the mesh above.
so the mesh contains things of different dimension.
Yes.
Is that correct?
Well, although we did say
Yes.
something, I think, about like, well, okay, never mind. I think with highlight graph, we talked about vertices and edges aren't
So,
the same, but
so
whatever.
if you take that mesh and then you say mesh cell or mesh count, we give you all the cells from dimension 0, 1, 2, 3, at least 1, 2,
Yeah,
3.
So
exactly.
if I say
Right.
mesh
But
count,
I guess
how do I do this? Is it mesh cell count?
Mesh cell or mesh cell count, yes. Of the
count is just a count.
Maybe I misunderstood earlier, but I thought you were saying that when
This
you
is the
run this,
number of cells of dimension 0, 1, and 2.
Yeah.
Okay, but I thought you said earlier that, and maybe I misunderstood, but I thought you were saying that it will delete things that are lower dimension. It'll delete all the cells that are at a lower dimension than the embedding dimension, or at least like if there's a line, if you do this annulus thing and then you delete those interior cells, but there's also this line segment that just goes off to the side, right? Just a lone edge that's not part of a triangle. My impression was that edge was going to get deleted, or is that not correct? Right, because if it is going to get deleted, then you're just ending up with a bunch of triangles. You're only going to have, you're only preserving the cells that contribute to a cell that's in the embedding dimension, and the circle case probably would return an empty region, right?
Is that what's right, Charles? I think without being able to run this, we can't really say. When will we be able to run it? Charles?
Well,
is there any version on which you can run it right now and show us these results?
Right now, we focus on the 3D, and the 3D should work on your machine, right? So,
well, it didn't work.
Oh, we can try it then.
It crashed.
No. So that was torus. We are working on adding torus. Random point doesn't yet support torus. So,
okay,
if you take
how can I take
take a sphere
okay.
or ball?
Okay, let's take a ball here.
And if we make the radius small enough, we'll start.
And there should be example in the documentation also showing that.
What's it doing?
Should probably take a few points. I mean, it's an expensive computation. Especially that in this case, you haven't specified this, the boundary. So we need to kind of find the best boundary to reconstruct it.
Okay, well, I don't think this is showing me very much other than that this is showing me a kind of a cruddy, okay, it looks like
what's the dimension? Test the region.
So this is dimension 3, the object is dimension 2, right? It's just a mesh region.
But I guess the question is, would it be possible that with the right inputs, you would have some line coming off of it? Like
I'm just utterly confused here. This says it's of dimension 2, so this is just the surface, it is not the volume. Is that correct?
Yes.
If I were to look inside, can I graphically go inside? Help. If I go inside.
No. That camera model that you're trying to use, that can't go inside. That's the old one.
Okay. All right. Okay.
I think if you
but it will be empty inside, correct? I mean, if I take a plot range and I would see there's nothing in it. If I slice it in the plot range, there'd be nothing in it, correct? It's just a shell.
Yes.
Is it a boundary mesh region or a mesh region?
Mesh region.
Yeah, because if it was a boundary mesh region, it would have dimension 3 here.
Okay, sure.
So the idea is that essentially when you have a set of points, right, you tend to want to reconstruct the surface, right? It's because, I mean, when you have an object, you can essentially sample the surface, right? And if you want it to be,
but it doesn't seem consistent. Oh, wait a minute, we don't have it in 2D. Because it then should do the same.
Well, we don't have it in 2D because it doesn't work
you were running Delaunay mesh. We didn't look at the right thing.
That was Delaunay mesh, right? So, if we ran this, if we ran it correctly, what we would see here is none of the. I asked you 3 times, do you see the shattered glass in the interior? And you said yes, but actually the answer is no. Is that correct? And what we would see instead is just the exterior and we would just see a thing that looks like the annulus without any shattered glass. It would contain the interior boundary and the exterior boundary, correct? Is that correct or not?
So I think the fundamental confusion here is
there's no confusion. I'm asking a very specific question. I want to know if this function was working correctly, would I see this interior shattered glass or not? Or would it instead look like, okay, so I don't understand this. This seems completely wrong.
I think
because in this case,
there is the
parameter
alpha. There is the parameter alpha. You are forgetting that it control. It's not a unique. It's not a unique object. I don't like care.
This thing right here is of infinitesimal thickness, correct? If I look inside here, there is not a thickened wall. If I were to poke through that face, I would be in the interior, right?
Can I explain something? Okay, so this example, right? Normally, you have to put a parameter alpha, which define the ball you are going to use.
I know that.
So depending on your the way you sample the point.
No, it's giving a definite output. There's a definite answer here. Either when I poke through that face, I get to the interior, or I don't, or I get to some thickened 3D object.
I agree. What I want to explain is that why we pick the input to be a mesh region. The input can also be a boundary mesh region. I'm trying to explain why we decide that by default we return a mesh region instead of the full dimension boundary mesh region, where in some cases it should be possible. Right? The function, right? So if you give him a ball, like in this case, you sample the ball dense enough, we can return you a boundary mesh region. Right? So the point in the design right now is, do we want to, in some case, return a boundary mesh region or a mesh region? The idea was that since everybody, and is a standard, people are doing surface reconstruction, so we return you the surface. Because surface reconstruction tend to think about a surface.
But then the 2D case should be curve reconstruction. And not, for that annulus, it should be the curve in that case. That's the analog.
That's perfect. We can go that way. That's
because you can't be inconsistent between the two, because that's,
Right. So let's go through the two cases, right? So case number one is we are reconstructing merely the surface, merely the boundary. Right.
Actually, wait, just to ask a quick question. I mean, if you made alpha 1 billion, would that still just be the boundary? Or would it maybe have some interior cells?
So for this construction of alpha set, when alpha get large, you get a convex hull.
Yeah.
Right, but you still only get the boundary.
So that means a convex hull is the full dimension.
Why?
Right?
Why? No, it's not.
No. Either we always do the surface or not. Doesn't matter what the alpha is.
That's why we picked mesh region, is what I'm trying to explain. That's why we decided to return you a mesh region and we stick with it.
Right. But if alpha is 1 billion and it returns the convex hull, is it the surface of the convex hull, or is it the convex hull as a full filled cell?
Yeah, it better just be the surface. Right? It's just better.
So how do I get that? I would say boundary mesh of, is that correct?
So in your example there, put 10, 20. Right, of the ball.
I don't understand this. I don't understand what just happened here. Why did I not get the pure
region boundary?
Region boundary.
Okay. Okay. So again, why didn't this? If I were using the correct convex hull, concave hull mesh, whatever we call it, I would expect that the analogy to getting this would be to get this.
Exactly.
Okay.
And I agree with you, and is in our universe of consistency, right? We like to have system think consistency, output consistent. But when people actually use it, right, in dimension 2, like somebody will sample, let's take a font, a glyph, S, you sample it, and then you say, give me the shape like
you're not selling me on this. Yeah, I understand what you're saying. That's look, if you want the interior, you need a different function that gives you the interior as well. One of these is giving you the surface, and one of you is giving the best reconstruction of the interior, including holes.
So maybe there should just be some reconstruct, boundary mesh and reconstruct mesh, or maybe those are the wrong names. Should be consistent. I mean,
So
there could just be two functions to do these different cases.
Yes.
Yeah, or at least being able to specify the goals.
but let's, what we are probably missing here, what I'm trying to say is that a mesh region can represent a boundary mesh region always.
Yes, of course.
There is no, so there
full
is no
interior structure.
So there is no inconsistency that example.
No. What you said was still inconsistent.
No.
The fact that in 2D, yes.
What I meant is the following: that ball example there, right? We are just right now disregarding the point. We can decide to actually return you the full tetrahedron inside.
Exactly. But yes.
So we have to decide which to do.
Exactly.
And we can't do a different thing in 2D and then in 3D.
I perfectly agree. That was exactly what I was saying. That is a matter of goal of what you want to use at the end. Right now, we just decided for the time being to just return the surface. We can actually run the construction to return you the full object.
Okay, all right, okay. So that means we've got two functions we're dealing with here. Okay, they are both filtered Delaunay meshes. Am I correct? They're both, you start from the Delaunay mesh and then you delete things, correct?
Correct.
So
although maybe just to know, I mean, in the case where you're only keeping the surface, right, the boundary, you're destroying most of the Delaunay mesh, right? All the triangles not all the triangles, but most of them are going to go away.
Right.
So the fact that the fact it comes from a Delaunay mesh at that point is probably pretty irrelevant.
Right. So the case where it was a full Delaunay mesh with holes above some size removed, right? That's one case. Is you've got a Delaunay mesh, you remove holes above some size, above some size. Correct? Is that correct?
Yes.
Okay. So one function that we have is some kind of, I wouldn't call it a wholly Delaunay mesh, but it's something which is based on Delaunay mesh, but with holes removed. That's case number one. Case number two is we're attempting to,
case number two is just region boundary of that, right?
That is correct. But which is also related to surface plot 3D.
So,
Yes, it's exactly that, isn't it? It's you remove the holes.
So, let's take the annulus on your left there. Scroll up just a tad. Let's say that we did a reconstruction and removed the holes. You then take the boundary of that. You get two circles, which is not the same as just. Sorry?
Which is not like the convex hull, where you get a region that is whatever this kind of region is, this one here, right? Where there's region, where there's interior in it.
So hold on. There's a more fundamental question, which is what is the input, right? So the input could either be, these are points sampled from the interior of the region, or it could be these are points sampled from the boundary, right?
Okay. So if you really allow me to explain, okay? So here, essentially, we are following a standard method of reconstructions, right? Which in some cases, it will carry those lower dimension or not, right? So for example, let's take the 3D case there. You have a ball, right? What normally we should return is that boundary mesh, which contains the interior, right? And if you run that same code, but with a sphere, we return you the surface.
It's just crazy. It just
no,
it's not crazy.
Sense.
It's a mesh.
That makes sense.
It makes sense. It's the object, right? So we pick to return you. Then instead of moving between a boundary mesh and a mesh region, we decided to return you, at least for now, a mesh region. And in this case of the ball, normally when we finish your implementation, we are going to give you actually the point inside. Right. So if somebody do a sphere, you have the sphere, we can construct.
I was just going to tell you that. Okay, but you're on that. Okay, fine.
Yeah. So it's what I mean is that we are, is that direction we are going, and we are preserving those points.
Yeah, that makes sense.
Okay, Roger, re-explain this to me. Oh, somebody re-explain.
Yeah. So here, the two cases. Like take ball and sphere. sphere. So a ball has a filled interior, a sphere is just a shell, right?
Mm-hmm.
Let's say that you're given points from a ball, you have a bunch of interior points. It makes sense when we reconstruct that we also have the interior.
Yes.
You know, tetrahedra. This one doesn't currently return it, but that's intention is that it would. If you have points from a sphere, you only really want the surface, right?
Mm-hmm.
And so in which case, that's what you want. You know, they should have dimension 2, like the thing that's been output from the ball.
Hold on. Let's just say I've got some experimental data and it really came from a sphere, but there's some noise in the data.
Yeah.
Is it a sphere or is it not a sphere?
Right.
I mean, is it
okay.
A 2D
this is where the alpha comes in, I think.
But
yes, but we can't change the return type depending on that value.
Well, we're gonna have to switch anyways at some point, right?
Why?
No, but that's why we wanted to.
No, I take it back.
Mesh region, we are not
Stephen.
changing the return.
Exactly. I was going to say, Stephen, we're not changing the return type. We're never returning a boundary mesh. We're always returning a mesh.
Even though the representation is not efficient, right? But return you the full mesh.
Yeah.
Okay. So,
but you see what I'm saying? The type is the very same.
All right. Okay. All right. So given all of this, what you're saying is this is essentially what would happen if we called this something like, you know, coarsened mesh or ball coarsened mesh?
I don't think it helps people. Do you?
Well,
I mean, first of all, I want to work. What it is. No, I want to sort of put some more work into the description of what it does. And
well, I think we know what it does basically at this point. It is making the Delaunay mesh.
But people can't call us, you know, and they would get confused if they did. So we need to write it down.
I know that, Roger, but I'm trying to get what is the qualitative description of what's going on. You are making.
I see.
You're making a mesh, and a Delaunay mesh, as it turns out, but we may not want to tell people it's a Delaunay mesh in the name. Right? You're making a Delaunay mesh, and then you are. Is it coarsening or what is it? It's a. What is the right word for something where a thing that is a whole is being dropped out? What would you call that? A porous Delaunay mesh. That's not right either, because porous suggests that there are pores in it, holes in it, if you understand what I mean, which they're not holes of that kind. It is.
So essentially what it's doing is fitting cells of a certain measure.
It's what? It's removing cells below a certain measure or above a certain measure. No, below us. What's it?
Yes, roughly, yeah, below. So kind of that fitting.
But that's not what's happening here. It's not doing that. It's
filling the edges that are above a certain measure. So actually, I mean, maybe this is off topic, but like, I mean, if you have, for example, 3D scanned, you know, point cloud data, right, where all the points are from the surface of the things you're looking at. I mean, that's a case where I think you would actually like to get a boundary mesh out. I mean, maybe there could be a different function for that, but I don't know. It just seems like that case is probably fairly common and worth supporting.
But you have no guarantee. Yes, but you have, you know, that's why we kind of stick with the surface, right? Because you have no guarantee that the reconstruction will be actually a closed volume. Same case like list surface plot 3D. But we have function, or we should actually add a function. We take a mesh and then generate the boundary mesh, the volume.
So I see. So okay. The problem is that it might not be a well-formed boundary mesh.
Exactly.
Right. It might have a giant hole in it. Yeah. Okay. Right. I see. Yeah.
Yes. We've done some of this. We want to come back
from where the stand of the rabbit. Is that right? Which you can't scan.
Yeah. For instance. So we repair mesh does some of that. Okay. for 3D printing. But when you take, I think there are more methods that one can use, basically.
But I guess kind of the point being though that that might mean though that we want to have a separate function maybe in the future that returns a boundary mesh and that really is a surface reconstruction thing. In which case this function could maybe be a more pure interior reconstruction thing.
No, let's not mix both, because the thought was that we'll have a reconstruct mesh which will have the different goal, and then the goal will be give me the surface or give me the full dimension object, right? Or the closed object or the object which satisfy the following criteria, and then we do the magic to generate you the reconstructed object, right? Where
there's a candidate page if you want to bring it up.
Right. Where in this scale of this convex hull mesh is a specific technique where there is, we return you that we have that construction and then we just return you the resulting object from it, right? So there's,
Sure.
This is a valuable construction, just like Delaunay is a valuable construction. The alpha shapes.
Of course, right? But if we're talking about the reconstruction thing, I guess I'm just like, it seems like there are two different cases here. One of them is you have a set of points on the boundary. One of them is you have a set of points on the interior. And it kind of, maybe I'm misunderstanding, in which case, just ignore me. But like, it sort of sounds like this function that we're trying to name right now is sort of like, in the 2D case, it's kind of assuming that the points are on the interior, and on the 3D case, it's sort of trying to handle both cases. And I'm not sure that makes sense.
No, so the key idea is the following, right? Well, because we tend to use Delaunay mesh, right? But it's essentially, if you have a set of points, right, and you construct the neighbors, right, you are going to get a cell, right? In 2D, you will get triangles. In 3D, you may get, triangle like for a sphere, or when you have a ball, you can actually get a tetrahedron because you have, closest point, right? And so based on those cells, you pick those ones who fit nicely a ball. And that's what helps you to reconstruct pretty much the original surface. So if you have a 3D object which have interior point, you'll be able to reconstruct those interior points. If the object is just purely a surface, so you just have triangle on the surface, then you don't have that volume, that volume inside.
Okay, so just out of curiosity, for imagining that this worked in n dimensions, just so we can see if it's consistent, right? So basically, you're constructing the n-dimensional Delaunay mesh, which consists of a bunch of n simplices, right, or
Yep.
something like that, right? And then what you're doing is you're selecting the edges that are length less than alpha, and then you're deleting all of the cells with dimension less than or equal to 1. Is that right? So you'll have
I don't think
2D surfaces, and you'll have 3D simplices, and you'll have 4D simplices, and so on.
So this function extends to a polytope in ND, definitely, right? But that technique of reconstruction of a Delaunay is easily visible, or most of the cases in 2D, really.
Right. The thing I'm just asking though is just that because it seems like, because my impression is that in 2D it is deleting if there's some lone edge poking out into space. After you've pruned out the edges that are longer than alpha. If there's one edge that doesn't get pruned out, but it doesn't have any associated triangle, that edge gets deleted. But then in 3D, if you have a triangle that's sort of on its own, that's not part of a simplex, it does not get deleted. So I guess my question is the rule just that things with dimension 1 or less get deleted, regardless of what the embedding dimension is? Or is the rule, kind of inconsistent between the embedding dimensions?
Okay, look.
Exactly. I thought we clarified that before, but
okay, I'm so irreducibly confused now, and several people on our live stream are adding their suggestions. And okay, let's go through again. What Okay, first of all, does it make sense in the future to have reconstructed mesh, reconstructed boundary mesh? Does that make sense?
I think that if you look in that page, we have a more general proposal than that.
The page called reconstruction mesh, is that correct?
Yes. And this is an early draft, but you can see sort of, it's called cons here. I would say goals, but.
Well, that's an interesting way to do it. So that will be a list of things that you want, like an orientable something or other. You'd give a bunch of constraints that you're trying to seek.
Right.
But then the returned object would be a boundary mesh, or it would be the interior mesh.
I think that that's another part of a goal that needs to be specified. So for instance, it's actually useful in reconstruction to say that you're seeking, let's say, a hypersurface, so a surface in 3D or a curve in 2D. I think that's a useful constraint, actually.
Sure.
Because it allows you, the question you just asked me, that the data is noisy.
Yeah, do you want the thickened thing with its interior, or do you just want the best 2D surface?
Right.
Right. So it's almost like there's simply a thing which is the dimension of the object that you want to get out. Is it the full, you're saying 2 or 3. In the case of the teapot, you might want, the best fit of the surface or the interior, or, okay. So I think
so you're basically saying the target dimension. Well, okay, I guess they're technically two different things. There's, I want a boundary mesh, which represents a 3D object with a 2D boundary. Or it could be, you're saying the object that I'm giving you points, the object you're trying to reconstruct, is of dimension 2, even though it's embedded in dimension 3. And I want you to return me a surface, which is a mesh region.
I would suspect we want reconstruction mesh and reconstruction boundary mesh as two separate functions, where the reconstruction boundary mesh returns a boundary mesh object and reconstruction mesh returns a mesh object.
Well, my claim is that we don't really need it, because we can always represent a boundary mesh as a mesh region. Right? Like we did for discretization, is because there you want an output with that form. But where in this case we can have both functions. I mean, there is no big difference. It's just one line of code to mix both.
This is it's not useful because you can always run boundary mesh and get the boundary mesh.
No, right. You can always, we have utility functions.
I think it's useful for the concept of the thing.
Okay.
But I'm not sure. But this function seems pretty reasonable. Okay. Now
it's a little raw. It's too raw. No, but
I understand that. I understand that. So the question is, what is this function, which is supposed to be? Now, which one of those is it going to be? It could be either of them, couldn't it? It could be either the one that is giving dimension 2 here or the one that's giving dimension 3 here. Am I correct?
Yeah.
Okay. So we got to figure out how we deal with that. And maybe it's two different functions, or maybe it's an argument to the function, but it can't just be we choose whichever one we feel like. Okay, so the question is the name something that is based on the word Delaunay mesh? I really don't like this ball idea. I think that's totally confusing because I think it suggests that the thing will be a composite of a bunch of balls, which will be a perfectly reasonable way to represent a region in space, but that's not this. Am I making sense?
It's not this.
Right, so we don't want the word ball in there, I don't think. So the question is, do we want Delaunay mesh in the name or not? Question. What do you think?
Well, I don't think we should have Delaunay mesh. Delaunay in the name. It's more a technique to reconstruct it. I mean.
Okay.
I mean, another way of thinking about it is Delaunay. I mean, Delaunay meshes relate to so many of these different constructions. I mean, even things like Voronoi meshes and stuff like that, where it's the dual. I mean, there are lots of things you would call a Delaunay mesh anytime it was this closely related.
Yeah. The other question, Charles, I mean, conceptually one can view it as a filtered Delaunay, but when I think one can construct it directly, right? And then.
Okay, fine. So the Delaunay is not in the name. Okay, so what is the description of this thing? It is a thing where there's a minimum cell size, right? Is that the right way to think about it?
Yes.
Is it cell size?
That's why I'm preferring these things like coarsened mesh and things.
It's not a coarsening though.
That kind of assume that coarsening, that means you already have something, right? Where here per se you don't. So we kind of build those cells and then do the coarsening, all the filtering after that.
What's the possibility of having this be the early version of reconstruction mesh with this being the default method and then adding constraints later for reconstruction mesh? I mean, you go ahead.
I really think we should have this as a standalone concept. It's
all right. Okay.
In computational geometry, it's almost as fundamental as Delaunay.
All right. Okay. Okay. Well, fine. But then it needs a name, and there need to be two versions of it, right? One that gives the boundary and one that gives the interior. Correct.
So if we're having it as its own function because it's sort of a known concept in computational geometry, I mean, at some level, then it should be named what it's called in computational geometry. But I think we decided that name was too crazy.
Which is concave Hall mesh.
Oh, for God's sake. No.
Yeah, or alpha shapes.
Oh, alpha shapes.
Oh, come on.
Right.
Yeah.
I mean, I feel like method arrow alpha shapes or something would be okay.
Yeah.
But it just feels a little.
It's just a crazy thing. It's just a crazy thing. It's some. It's probably a brand name for some type of 3D scanner or something at some point. I don't know. Who knows what it was, but it's not an interesting name. And also the alpha parameter is the wrong way up.
You know, one thing that just struck me is the guy that came up with alpha shapes is this guy, Edelsbrunner, who was a professor at U of I.
Yes, we know him. Yeah.
And then he did a spin-off company that did reconstruction.
Indeed. Fancy that.
Probably using alpha shapes. Well, I mean,
I'm
you want to call it.
I'm thinking, I mean, that wasn't because it was, it was doing it was constructing NURBS and CAD models and stuff in the end. But
so maybe it should be called, what was his name?
Edelsbrunner
mesh or something.
Good point. Going eponymous all the way.
Well, it's what we would do for special functions.
Right. Well, why not?
Because nobody will know what it is. And because it probably had multiple origins and we have to research that. I mean, not that,
Not that Delaunay was the first with Delaunay.
No doubt. But we're using sort of conventional names and that one isn't one. Okay, what are we going to call this thing? I mean, concave Hall mesh is just a stupid, plus it's not even describing. How would we deal with the surface versus interior question? What would be let's imagine that we used concave Hall mesh, which I don't think is a good idea. But if we did that, how do we deal with the surface versus interior?
Yeah,
Charles?
You mean in the term of the name or in the term of the output?
No, Neither. We need both cases, right? We need both. It produces the interior and it produces the surface, right? We need both of those, not switched automatically. That's not what we're going to do. That's what we're going to do for reconstruction mesh with its second argument, but not for this. This is supposed to be a building block function that does not automatically decide what dimension its output is.
I mean, I normally hate eponymous names.
To say that the function doesn't change the dimension. We are not changing. We are following a process, a standard construction, same as a special function.
No, it's not right. It's not right. In this case, does it have an interior or not? Right? That is something you can't choose differently, whether this has an interior or this has an interior. No, it's either they're both surfaces or they're both with the interior. Am I missing something here? Roger, can you confirm that?
I agree.
Okay, so we've got two different things. Does it have the interior or does it not have the interior? Correct? Am I missing anything here?
So, I mean, maybe it could just have an argument. You know, it has the mesh, it has the radius, and then has a third argument, which I think, you know, which would basically be the dimension. What would you say? Basically, the minimum dimension of any cell that it keeps, right? So all the cells with lower dimension it deletes, which is I think is how you would get the boundary as opposed to getting the interior. Right. So if you wanted the boundary in this annulus case, you'd say, you know, whatever mesh of your points, comma, automatic, comma, and then you'd say 1, and it would give you just the curve. And if you said 2, then it would give you the actual annulus.
So
which is the okay.
So if you allow me to say it again, and you know, maybe we are going to loop again the same discussion, right? So this is a specific method construction, right?
I don't care.
Which is fine.
I don't care. I don't care that people have conventionally done this or that. Nobody is going to understand it. The fact that we've spent an hour and a half talking about it is a very, very bad sign in terms of anybody else's ability to understand it.
I was about to talk about the resulting output, not the name.
Okay.
The resulting output, somebody can come and say the result of the following function, whatever we call it, it's wrong. I will, you know, it'll be easy and clear to justify it. And so essentially the construction, at least the standard construction, is from the Delaunay triangularization, where you cover the cells and then you take the cells inside the ball. There is no ambiguity there. The cells you are picking are precise. So that means we know exactly the n-dimension object you are generating. It's not related to the representation we have in the Wolfram language that we return a boundary mesh or a mesh region.
Right,
it's a specific Rn object.
Right, that makes sense, right? But I think that the case where it's breaking down is just that after you do the important step of selecting the edges, you know, the edges that are not the simplices, but the edges that are, you know,
no,
length,
but Christopher, you're thinking about edges in dimension 2, and then you jump in dimension n. That's not the same.
Oh, so in dimension n, are you not selecting? Are you selecting, you know, triangles?
You look at the d-1 face, the d-1 cell, because in the when you look at the, you know, polytopes, right? You describe them with the d-1 cells. In dimension 2, you describe it with the, you know, d-1, which is the edges in your case.
Oh,
in dimension,
okay.
Right. So there is that cell structure.
This was the thing I didn't understand this entire time. Okay, so in 3D, it's not selecting edges, or it's not deleting edges, it's deleting triangles. Is that right?
Exactly. That's cells. That's why for the sphere you can have that object, that, you know, that surface to that construction.
Okay, thank you. That was the thing I did not understand the entire time. Okay, now it actually makes sense.
Can you explain this to me?
Okay, the point just being that it's and that's also why that picture you had in the documentation, that's actually probably the nicer picture to show. Okay, so basically it's just that it's instead of just filtering the edges, it's filtering the simplices and, you know, the d-1 dimension cells. right? I mean, like Charles just said.
Yeah.
So in 3D, you're deleting triangles, right? So you're going to end up with some set of, so right, in 2D, you're deleting edges, and in 3D, you're deleting triangles. And so if you delete a bunch of triangles, you're going to end up, you could end up with just a surface. Or you might end up with some cells where, some tetrahedrons where all 4 of their triangles have survived.
Well, what happens to a tetrahedron which has one face removed? What do you do with the tetrahedron?
It's a tetrahedron with a face missing. It's got a hole in it.
But then it isn't a tetrahedron.
Well, right. So
then it's just the surfaces of the tetrahedron.
Yes.
So, I mean, the water fell out of the tetrahedron in that case.
Right. But so I guess, right. I mean, in terms of how it's actually represented, I mean, so I guess the point is, if a tetrahedron keeps all of its faces, does it remain a solid tetrahedron? But then if it loses one, it all of a sudden becomes a shell? Or
yeah, what does happen in that case?
That's why we decided to return it as a mesh region, right? Then in that case, you are losing,
Okay, so as a mesh region, it goes from a three-dimensional mesh, three-dimensional cell that is the tetrahedron to, let's say it has one face removed, to 3 two-dimensional cells that are just faces. Is that correct?
Yes, so mesh region can represent all those dimensions.
I know it can represent all those things. It can represent cells of different dimensions.
And if I think that's probably okay, right? Because it's just, if you have high enough resolution points, then it doesn't matter.
But there will be a value to filtering the output so that it is only a thing of a given dimension. Because if you think you want a surface, you don't want random extra little tetrahedra in your surface as little, hard bits, so to speak. Am I making sense? If you want a freaking surface, you want a surface. You do not want tetrahedra embedded in your surface.
But I think that then that's not this construction.
We should have utility to filter, right? We have,
Yeah, that's what I mean.
It's not a question.
Additional processes need to happen.
Okay, you've got a surface, and somewhere in that surface, there are little embedded tetrahedra because your data was a little bit too fuzzy in that region, right?
Yeah.
It's a Gaussian noise thing, and your alpha value was such that blah, blah, blah.
Absolutely.
Okay, so now what do you do with that?
So that's why we'll have several reconstruction functions.
No. That's not an answer. In this particular case, I want to know, what do we do with that? How do we turn that into the pure surface?
This one, I think,
in this case, it doesn't handle the noises, is what I want to say. This is a specific method. There is no
This is like Delaunay.
Handling.
It's a specific construction.
I know that. So I'm asking the question, how would you go from the thing reconstructed by this that has a surface with random tetrahedral bits in it? What do you do next?
I think it's just you don't, right? I mean, it's just, that's a different function. This function leaves you the tetrahedral bits. And, if you're doing computational geometry, you want them anyway.
Okay.
Right? If you're studying alpha shapes, you want the tetrahedral bits.
All right. So this is a mesh where you are keeping everything. It is some kind of thresholded mesh. Is that a fair way to say it? Where you don't keep a cell that is below a certain size, right? Is that the correct thing to say?
And where the cells are in D-1 dimensions, where D is the embedding dimension.
Right. Is that right? I mean, what's the right term? If this was image processing, what would you be doing? It's a blurred mesh of some kind. What's the concept? Right. What are other cases where you are removing things below a certain feature size? Pruned. I mean, what about something like?
I mean, it's more like it's removing things that are too far apart. They're not.
Right. Right. That is right. I mean, it's removing things. Okay, so it is. This is hopeless. I mean, this is okay. The name reconstructed mesh, for example, that's a perfectly good name, I think.
But that needs additional work. But I agree with you.
So maybe we have to go with concave hull. Yuck. Yuck.
Is that name much more popular than alpha shapes?
I haven't tested it.
Well, it's the one people use for reconstructions. Yes, it's more convenient.
Oh, so you call them alpha shapes if you're doing something other than reconstructions, basically.
Well, you call it alpha shape when you want to reconstruct. You want to describe that family of objects you are getting, right? So.
Oh, okay, so the object it produces is an alpha shape.
Exactly. So it's it's a family.
But the algorithm. Okay, but the process is this convex hull mesh.
Concave.
Concave. Yeah.
So the other thing, that gradient mesh, that you like that name.
I mean, it's at least nice in that it tells you what it takes as its argument.
Or gradient fit mesh.
No, I think gradient. Well, the only problem with gradient mesh is you might think it's something like boundary mesh. Why would it be gradient fit mesh?
Because we are actually fitting the gradient. Right. Where gradient mesh may think that, like you say, or it's kind of a tangent, a differential geometry type of mesh you get from by computing the tangent space.
What do you mean by you fitting the mesh? You are making it. You are given a bunch of gradients. Is that correct?
Yes.
Yeah.
And then you compute that fit, that mesh where you have the best fit.
I think gradient mesh is okay.
Could it be called tangent mesh? I mean, because the mesh is also tangent to all of the vectors you're giving it, right?
But we tend to use gradient, right, as explicit value than tangent.
It's tangent to the orthogonal complement to it. I mean, it's.
By the way, for a comment for various people on live stream like Sander, convex hull we have. The issue is what to do with this thing that isn't the convex hull, that is selecting out things that are non-convex hull. I mean, what it's been called in the. Go ahead.
No, sorry. I mean, I'm just right. It's basically just reconstruction, but the problem is that the non-convex hull mesh is not, might actually be convex.
So isn't that lovely? So can a concave thing actually be convex?
No, unless.
Okay, then why is it called concave hull mesh if it can actually be convex?
Okay. It's like saying if something is non-decreasing, can it also be non-increasing? Yes, it can, if it's zero.
It's like how non-linear model fit can return you a linear model.
Oh.
Yes, it's like can something be convex and concave? Yes, if it's linear.
Okay, so you're arguing. Okay, the question is. Okay, so. The possibilities here seem to. So the first point is reconstructed mesh or reconstruction mesh, not completely clear which one is right, is
a project for the future.
Hopefully soon.
Very soon, yes. But
okay. But so the question now is, we are basically making something that's going to have a ridiculously technical name. By the way, if we were going to create gradient fitted mesh, wouldn't that be the right term? Not gradient fit mesh, gradient fitted mesh.
Yes,
Isn't that the right?
I guess so. Yeah.
I think that's actually a better name than gradient mesh. It removes one confusion.
Isn't that too close with the fitted mesh?
What is fitted mesh?
Fitted region.
Thing we made last time.
Oh, fitted region, right. Oh, sorry, yeah, that's fine.
Which does what?
Well, it fits parametric regions, like
Parametric regions.
disk, like line.
Right. But this fits a mesh to gradients, correct?
Yes.
Yes.
Well, so should it be gradient mesh and we don't try to explain the fitting thing, or should it be gradient fitted mesh?
I kind of tend to agree with gradient fitted sounds, it's a little longer, but it says what it does.
And it will be similar to the fitted region and reconstructed mesh. And
but is it correctly similar to that? Are you supporting this name, Charles?
yes.
Okay, all right, let's go with that.
And the first order necessary conditions is the Poisson equation. That's why it was called Poisson mesh before.
Where am I keeping all this stuff? Geometry.
You could save it there. That's fine. I think last time you emailed it, but
Copy this stuff in there. Okay, so we've got now. So I think reconstructed region and reconstructed mesh and probably for the future approximated either reconstruction mesh and approximation mesh.
Or approximated, presumably, if it's going to follow the same idea.
Yeah, right. It's either approximation or approximated mesh. Reconstructed mesh and approximated mesh seem like the better thing to me. Okay, so now the question is what to call this creature right now. And
I think we have the names now. I mean,
the concave hull thing.
Yeah.
All right, an hour and a half later, we come back to where we started from. All right, I don't see an alternative because I don't think there's anything else. Any other name we come up with, we have to develop a whole story behind. And we're going to do that for reconstructed mesh and approximated mesh, but we won't do it for the more technical thing.
Right.
All right, fine.
Maybe there should be a note in the details that says that concave hull mesh may return a convex hull or may return a convex mesh or something.
Yes, it should definitely say that.
Definitely. Yep.
God, it's a terrible name. Okay, one last time. Any other thoughts about what this could be?
I mean, I feel like if the point is that this is a thing that people who know computational geometry will be using, and other people will be using reconstructed, whatever mesh, then it has to be either called concave hull or alpha shapes. And alpha shapes is crazy.
Could it get away with non-convex hull?
No.
That has the same problem anyway.
No, I know it does.
No,
Well,
I
now
agree
I've
with you,
changed
Christopher.
to
That's how I
concave
do it as well.
Mesh.
Yeah. Yeah, right.
All right. Concave hull mesh, I guess it is. Splurf. All right, let's get to reconstructed mesh and approximated mesh as soon as we can. Like next version, right? Is that realistic? Roger?
I think so.
Okay, fine. Let's just look very quickly at these other things, see if we can get through at least the geometry part of this, and then we've got another, whoops, region convert, right?
So
what is this for, really? This
is an
essentially
incredibly
internal...
useful utility function for people that do programming with geometry. It allows you to convert between different representations. We've had this hidden underneath this multi-representation, and people keep asking for it all the time. So this is the kind of thing you want to use a lot when you start programming geometry.
It is very interesting that we've never had to have a thing like this for graphs. But that's been a successful place where we can hide the internal representation.
Well, no, I mean, we have a bunch of things for graph. You can get matrices, you can get incidence matrices, adjacency matrices.
Fair enough.
All kinds of things. But geometry is a sort of an order of magnitude more complex in the sense that there is no one finite representation. And not only that, the downstream clients for compute, they require different kinds of things depending on, which theory it is. So for instance, if you're going to integrate over a region, there is no implicit definition. You have to have a parametric representation. In differential geometry, they use the implicit function theorem to get a locally parametric representation.
Yeah.
It requires a parametric representation. If you do optimization, it's all done with implicit representation. That's how constraints are done in optimization. And so you'll find this repeatedly in all kinds of places that the compute side, a domain or a community is homed in on a particular kind of representation, and you need to be able to flip between them.
Okay, fine. Let's go through a few of these. Why you say solid torus, then you immediately describe it as filled torus.
Yeah.
We have solid anything? Do we use the name solid for anything?
We probably don't, actually.
So didn't we already have torus or no?
No.
Oh, okay.
Well, so we've got ball versus sphere, disk versus circle. What's an annulus? Annulus is the interior region.
Annulus is filled, yeah. Annulus is sort of like the 2D torus in a way. Kind of.
2D filled torus.
Yes.
I mean, the analog here will be some kind of ring type thing, but that's a really stupid idea.
Yes.
I think filled torus is better than solid torus, especially since presumably it can be a torus in any dimensions.
No.
Why not? I mean, in principle, we don't have to support it today, but in principle, this could be an n torus, could it not? Which involves a product of n circles. Am I confused?
Maybe you're right.
Can you run filled filled star or fill star or something?
We have filled curve.
A filled curve is very much like this same concept for a filled torus, is it not?
Yes.
The spacing is, could whoever's PMing here just make a note of this? This just really goofed up. The way that spacing works. Why is this
marked it down?
Right, the spacing is wrong, the font size is wrong. Come on, we can do better. Filled torus seems better to me to go along with filled curve. Okay, so these things, there is no visible change other than that we can compute volumes of these things and lengths of them and so on, right?
Yeah, and you use them in a whole compute framework, the whole compute geometry framework.
I know, it's very impressive. I mean, I'm sure has no documentation impact, but a very impressive piece of implementation.
Yeah, I mean, as a matter of fact, we do, if you go and look at their primitives, they have sort of two sides to the documentation examples. There's a compute side and there's the rendering side.
I was just looking, but yeah, right. I don't think it's in there yet.
No, not yet. Not
Okay.
for these new ones. And it needs sort of a refresh, like we did for all the other ones when we introduced geometry.
Okay. Let's just have a quick look at geometric. Wait a minute. Geometric transformation. What's the difference between that and the?
So those
disaster?
first group there were only applicable to in graphics and graphics 3D, and we now accept them in geometry, so they can be used. You know.
So
like
you can take a sphere, for example, and I could say, if I say something like, you're telling me that what I could do here is say something like this. And well, and you're saying if I do this.
Arc length, for instance. Arc length for that, for instance.
How would I compute this just numerically?
You integrate.
No. I know what the calculation is. I'm asking you here, if I wanted this to be just a numerical computation rather than the symbolic thing it's trying and failing to do.
Working precision.
Right.
Oh, nobody will ever know that.
Or can you just say n of the shearing transform?
Would it automatically go to numeric methods if it's approximate? If it's finite precision?
Yes, it should. And actually here it should. I think it's, we are still working on the, refining it, but it should, figure out if it can do the integration fast enough.
Okay, fine. So that's lovely. But now, so, and if
why is that so slow? It's just an F.
No.
I should use.
Well.
Well, let's go. You and
yes,
I can.
Okay. Yeah, we'll figure that out. Yeah.
I'm surprised. Okay.
Yeah,
so
it's
that's lovely.
Fine thing. Yep.
Okay, what is region transform?
Okay, that's a totally different thing.
How can it be such a similar name and be totally different?
It finds a transform. Okay, so if you use translation transform, rotation transform, all of those things produce transforms, right?
So why isn't it called find region transformation?
I think it should be probably.
Actually, that's the name we haven't updated. That was the final name we proposed.
Well, actually, why is it
region
not?
Yeah.
Hold on. Doesn't find geometric transform or find geometric transportation, whatever it's called, doesn't it already take graphics primitives or something like that?
No.
No, but that's a good point actually, where we discuss about, we have been, looking at this. So find geometric transform, it actually does more a fitting problem than actually finding the transformation. So find region transform give you the actual transformation, or at least one of them, right, between two regions, where this one does a fitting. And if you also look at the function, the output is actually the output is the inverse transform, right? Because you give the mapping from P2 to P1.
So it's because the convention is backwards for images,
right,
if you recall.
Yep. So it's kind of highly custom.
This is obviously another discussion. We need to schedule yet another.
Yeah, and that is basically to find, so the two things congruent is when there is a rigid transform between two regions, and a similar, two regions are similar when there is a rigid plus scaling.
Right, but these things here, these are tests, and that's fine.
Right, the region transform or find region transform is the one that actually finds it if you want the mapping.
Right. So, I mean, it should, okay, but we got to understand the relationship for find geometric transform.
Sure.
By the way, one other reason why it should be find region transform or something like that, and not region transform, is that don't we already have like transformed region? And it would
Yes, we do.
okay, I would always accidentally use region transform instead of transformed region if both of them existed.
Right. This thing is output transform. The other one is output region.
Right.
Right. But so transformed region does what? And how does it relate to all of these?
You take a region and you transform it with some affine or linear or non-linear mapping.
Okay, and then the result of that would be
a new region.
Yeah,
so whether it can represent it in closed form or not, it is a new region as it is. Do you know what I'm saying? That representation is a region.
So sometimes it comes back unevaluated.
Exactly. Most of the time.
Well, it's not that it's coming back unevaluated. Transform region represent the region. It's just that it auto-evaluates. It auto-evaluates, which is different.
Right. So the transformed region could often be region congruent. By the way, does region congruent return conditions? Is that why it's not a Q function?
Yes.
So it'll give you.
You can't have Q functions for things with parameters. They become.
No, I understand that. I understand that. But so this becomes like a reduce type thing. Right. This can say if the angle alpha is 90 degrees, then it will be congruent. Otherwise, it won't be. Correct?
Yes.
Which is nice. And how does it relate to the congruent stuff that's in the geometric assertion business and so on?
Well, congruent should always mean the same thing.
No, Roger, I don't care. I'm asking you. There's a whole big system that's been built for synthetic geometry. How does what you have built here relate to that? Do you understand the question? Right? So like geometric assertion and so on. Have you talked to those people?
That sounds like an assertion.
That one is an assertion, but there's a related test. Right? What's the related test? Geometric test. Okay.
Try to give it a few regions and see if it can compute anything.
No, it can't do anything with region, right? But it has the concept of congruent and so on, right?
Right. And
the objects are congruent.
I haven't checked, but in principle, they should coincide the output. So I will make sure
make sure it does, and make sure that both things get to use each other. Am I making sense?
Yes, definitely.
Okay, we still need to talk about these transform things. And I just want to look ahead at these because this looks like a lovely idea. Let me just see that. And then we have to wrap and go to our next meeting, which is also a live stream about video. So where's the example? Do we have examples yet for this?
Not yet.
But so the way this will work, it will say lighting arrow and then a symbolic list of spotlights and things. Is that correct?
Yes.
That's lovely.
But then you can also have them in line in the scene.
Inline.
I see. So in other words, you can differently light different parts of the scene.
Yes.
But didn't we add that capability several versions ago?
Yeah. So you can have lighting goes to a list of things in line, which is very strange.
Very, very, very strange. Yes. That's very crazy strange.
And this one is more kind of additive, right? So you can actually make a nested sequence. Right?
I see. So you can have. Go ahead.
Yeah, go ahead. Go ahead.
Oh, all right. I mean, I'm just. So you can have it in style as well, presumably.
Yes.
Yes.
But now what happens if you want 3-point lighting for this part of the scene and you want something else for another part of the scene? How do you do that with these primitives?
You mean like you want one object lit with one set of lights and another object lit with another set of lights?
We got bank switched lighting descriptions for the lighting option. I'm asking, how do you bring those in to the style for an individual object in the scene?
Well, so you can, so the 3-point light is actually directional light. So you can do, directional light, 3-point light, right? And if you want to have it in different scene, you can control the scope by, the list.
But it isn't necessarily, there's no guarantee that one of these bank switched lighting settings is just one type of this. Do you see what I'm saying? Right? There's no guarantee of that.
Yes, there's no guarantee.
Right. So what we should have is some kind of primitive that might have been called lighting, except that that isn't the right. I mean, it's like color data, right? It's something like color data where there isn't quite the same thing either, but some primitive that is an inline primitive that can be put into style. Oh, actually, no. What am I saying? What am I saying? There's an obvious way to do this, right? All you have to do is to allow style to take lighting, and then you're done. Like this, right? Then that's how you put it in. See what I'm saying?
That's a possibility.
Yes.
That seems the right thing. Okay, there's a few comments on our live stream, and then we need to wrap up. And Ali is asking for the Voronoi mesh in 3D, which is coming, right, guys?
Yes.
It's going to be there in this version. Right, guys?
Yes.
Yippee. Long awaited. Voronoi mesh 3D. That's one of those cheer moments. Okay. Geometric scene 3D, Mohammed is asking for. Yeah, well, that's hard. Oh, Sandra is saying that style, sphere, lighting arrow, whatever already works.
Yes.
Well, so what are we talking about? So that then there's no problem with this. Then we don't need an inline primitive there. So it was saying graphics 3D of this. I don't know what the lighting specification. What? Give me 2 lighting specifications, please.
Well, accent.
And another one, please.
Neutral.
What do you know? Just worked. Great. Lovely. And so then the alternative to this would be to be able to say something like, in here, just spotlight. Is that right? I would say it here, or where would I say it?
Either there or as a
just
inline before, like color.
Right. What's its argument? Is it a position?
Position.
Not happy. What's it saying here? An improperly formatted directive with head spotlight was encountered. So something is wrong. I assume it is supported in style, right? It needs to be, right?
Yeah, we'll check that.
I think you.
Does it work if you say lighting arrow, spotlight?
Well, let's just try this. This is the inline version.
So it's probably taking the color. Sorry, spotlight take first a color and then the position. Oops.
Well, okay. Not yet working. Okay, one last thing here from Doug. Find geometric transform from points 1 to points 2 is already a function. Okay, find region transform seems appropriate.
That's
okay. If there's one canonical transformation between regions, I mean, clearly, if I mean, one of the issues which no doubt we'll talk about next time is if you have the cutout of the elephant and it is more or less rigidly rotated, but actually you distorted the piece of paper slightly, what does it do?
You will fail. You will find with exact transform. So,
well, but what if it's numerical data? What if the elephant is outlined with approximate numbers?
Well, we'll work with approximate number, but we don't handle noise or anything like that. So
but there must be a tolerance of some kind.
But I mean, by default, we use the system tolerance, which is 10 to the minus 12 from the numerical error.
Okay, but
we can add it.
Okay, so it's only rigid. So you're saying it is only rigid transformations that work?
Yes.
And similar.
And similar.
Okay. Similar transformations.
We need to talk about it some more, because clearly that's useful to have something which can work when there is some deformation.
Right. That's not called. I mean, yes, it is. It is useful, but that's not quite what these guys do. Okay, at this stage.
Okay, fine, but maybe that's what they will do in the future, and that's okay.
Well, maybe not these ones, but some other thing that recognize.
But we're not going to burn this name. Yeah.
But find geometric transform finds an approximate thing though, right? Like it doesn't care that they be exactly right.
But that's why I say the fitting. It does a fitting.
Yes, I know, exactly. But so you can't have a function called find geometric transform and another one called find region transform that do bizarrely similar but different things. So we need a further discussion about this.
Yep, we agree. Yep.
Okay, all right. For those following these live streams, we will be continuing with one about video primarily, right? Or did we finish the video segment and now onto image processing?
We have a little bit of video left.
Okay, and we'll be back to that in 5 minutes or so.
Okay.